The title of this talk is Python and Johnny Cash. The subtitle is that programming is or can be subversive. We're at PyData London. It's Saturday, May 17th, 2016. So, hello, I'm James Powell. You can say hi, James. I appreciate that. For those of you who are lovers of Johnny Cash, you know that he started many of his concerts with "Hello, I'm Johnny Cash," and he'd go straight into Folsom Prison Blues. For me, I would say that Python is something of an occupation and a hobby. I do get paid money to write Python code, although the Python code that I write for work is not quite what I show you in these presentations. I do spend a lot of my free time writing code for fun, to explore new ideas. I find that writing code, and especially writing Python, is something that can be very enjoyable. It's very fun for me. It's exciting, it's thrilling. I get to explore new worlds and new ideas and new thoughts. I like programming, and I like programming in Python because it's an opportunity for me to find a balance between following and breaking rules, between ignoring the rules and bending the rules and figuring out what you can do that people tell you shouldn't or can't do. Many of the presentations that I've given previously at events like this were the result of somebody telling me, no, you can't really do that in Python, or you shouldn't do that in Python, and me wanting to prove them wrong. In this sense, I could say that I like the subversive side of Python, and I like the subversive side of programming in general. I would say that outside of the costume that I'm wearing here, we all know that Johnny Cash was the man in black. I probably am the most subversively dressed person here. After all, I'm a guy in a suit at a programming conference. I actually think that Python is a very subversive language, if you think about it. I do a lot of corporate training, and one of the call and response that I do in corporate training is I ask the class, is Python a serious and grown-up language? And I don't think it is. I think Python is a silly and fun language. It's full of Easter eggs. It's made to be enjoyed. But then I asked them, is Python a language which can do serious and grown-up things? And while it's a silly and fun language, you can do very serious work with Python. Here in this presentation, at the end of the day, I'm going to show you something that the more I look at it, the more serious work I see can be done with it. There's actually a set piece for this entire talk. And when I was putting the set piece together late last night, I found that I didn't feel it was compelling enough to present it to you by itself. So there's a little bit of additional lead up. Now, I will tell you that the title of this talk was a joke. The title of this joke was a talk. When preparing my talk for this event, I couldn't figure out a title, and I couldn't figure out exactly the angle I wanted to tackle. I asked the Executive Director of NumFOCUS, Leah Silin, who I hope you all have an opportunity to speak to sometime during this weekend. Please take the time to thank her for all of her tireless work and for all of the work put on by NumFOCUS to make this event possible. She's a fan of Johnny Cash. In fact, she might not tell you this, but she shares a birthday with Johnny Cash. This is why every year I have forgotten her birthday. And she put me on the spot. So let's see if we can make it work. So I do apologize to fans of analogies. It's going to get a little strained in here. But we can also have some fun. It is the end of the day. So for those of you who here doesn't know who Johnny Cash is? Who here is too embarrassed to admit they don't know who Johnny Cash is? OK, a couple of people. He's a very famous American, I'd say country musician. He was actually a singer-songwriter. When I play some of the songs for you, I think you'll recognize them. In fact, let me start off with one song by Johnny Cash, one of his most famous songs, a song I've been humming all day, which is I Walk the Line. And you can see that this talk may walk the line between good taste and bad taste, between a meaningful analogy and a strained analogy, but nevertheless, we'll play a little bit of Johnny Cash for you.
I find it very, very easy to be true.
Who hasn't ever heard this song?
Alone when each day's through.
We'll convert you by the end.
That I'm a fool for you.
Who's ever seen somebody play mPlayer through an IPython notebook? Isn't that bizarre? Very good. So one thing that we know, one way that we walk the line in Python is we're encouraged in Python to do things like monkey patching. And we've all seen some instances of monkey patching. One very preposterous example that every beginner Python person tries is they see there's a function called len. They can pass it a list with 3 elements, and they say, wait a moment, I can override overload, override all sorts of functions, maybe I could override len. So I could write something like this, and I could say, well, instead of returning the length of an object, return the length plus 1. That'll really make my coworkers pause for a second, if not outright hate me. And then when you call it on 1, 2, 3, suddenly you get a result that you completely don't expect, and you say, wow, this is a very powerful language. In previous versions of Python, this talk is given in Python 3, but in Python 2, you could do things like say true, false equals false, true, and all sorts of absurdities. It turns out that these kind of monkey patching is a clever technique, but especially when it comes to the monkey patching of built-ins, it's not actually particularly useful. It is, however, useful in illustrating to us one of the reasons why Python is so flexible, which is that Python has a very rich runtime. When contrasting Python with a language like C, C++, or Java, one of the major things that we see is that Python is almost entirely runtime with only a very small component that you might consider to be compile time. People often complain that Python has no compile time checks. That's not quite correct. Python has checks, at least for grammar. The parser makes sure that there's no parser errors. And that occurs. It's something that you can consider compile time. There's a couple of other checks that you could do at parser time. If you're a fan of Vim plugins like Syntactic, you can do name checks at something akin to compile time to make sure there are no name errors. But outside of that, almost everything occurs at runtime. This makes for an incredibly flexible language where you can do a lot of neat things. One thing that we see is that Python is full of, I wouldn't say exploitations of its rich runtime, but practical applications of what you could do if you had a rich runtime. So for every intermediate Python user, you probably stumbled across a module like inspect. And you said, this is really neat. I can use the inspect module to do things like view the source code for a given function. I can figure out where a function comes from. I couldn't really do that in C because a function doesn't exist at runtime in C. It's just a bunch of assembly instructions plus maybe some dwarf debugging information. But there's no concrete entity at runtime to represent this. Whereas in Python, I can do all sorts of neat things. In fact, in Python, I can actually look at my stack. I can get the current frame for the function. I can look at the outer frames. And you can kind of do this in C and C++ with libraries like libunwind. But the compiler could easily eliminate stack frames or easily perform some optimization that would obscure your view of what's happening. Whereas in Python, it's easy. We have some function called g. We have some function called f. When we call f, it calls g inside. We can use current frame and get outer frames to peek into the frame of our caller and to look at variables. And to, in the previous example, you can see we had this x variable. It was 1, 2, 3. We printed it out. It printed out 1, 2, 3. Inside g, we can look up one frame, mutate x, and we get a totally different result. And this is something that people wouldn't expect. And in fact, this technique is probably even more obscure than our basic monkey patching. I will say that I have used this technique as a very, very last-minute, last-ditch effort at fixing a system very late at night where I wanted to do something incredibly surgically that I knew that if I woke up in the morning, I would go fix it. And if I didn't, then what can you do? I died a happy man. Now, one interesting thing is this breaks in a couple of weird ways. This won't work with value types. It's an exercise to the reader why this doesn't work with value types. The reason is that the local scope is shadowed by fast locals. But it's not that important. What we can see is that we have a very rich runtime in Python, and we can use it for other things. If you look in the sys module, might be the next place you go. You see things like setTrace and setProfile, and you can set functions that get called every time a Python function gets called. Here's a simple trace that just prints out every time this tracing function gets called. And you can see when you run in the IPython notebook, it sure is an awful lot of function calls to do not a whole lot of work. In fact, if I just do x equals 10, it sure is an awful lot of function calls just to get this x equals 10 to evaluate in my IPython notebook. You can see we have triggered some code hooked on every execution according to the Python interpreter for where the tracing function should run. Before we continue with the presentation, of course, we have to turn this off because otherwise it will completely blow up our notebook. The other thing that we can see is there are some explicit places where we have hooks in Python. In fact, if we think of Python as a language that emerged from a lot of people who had been writing systems in C, C++, and Java for many years, finding common patterns in that, and realizing that in large mature systems, we always need some safety valve, some hook, to address maybe one issue that got missed in design, or to work around some patch, or to work around some small issue to patch some small thing. Well, we might design it with safety hatches. If you look at physical construction is full of these safety valves, these escape hatches, ways to make sure that if there's a mistake in the original design, you can account for it. And an example of that would be sys.metapath. You can add import hooks in Python. So here's a simple example. This is a simple import hook. If the user accidentally misspells math or random when trying to import these modules, it corrects that for them. And it's a very simple thing. We hook into the import system. Whenever you try and import a module, we run our custom code. It's not particularly interesting. You can see I accidentally misspell the math module, and I get the right thing. I accidentally misspell the random module, and I get the right thing. This can actually be used for some very effective things. You can see that not metapath, but path hooks are actually used in some very large organizations in order to store all the source code in some sort of object database and to load it real time so that you never have to distribute source code to your users via some other mechanism. The application only has a very small stub that will then automatically load all the source code as needed. You can also do some neat things, and this is something that I prototyped for somebody. They were refactoring their code base. They wanted to move some modules. They wanted to change the names of some modules. And I told them in about 20 minutes and I'd say about 40, 50 lines of code, I could write you a really simple import hook that you could rename modules. So here you can see that if you have a module called moth, you can rename it to math, and you can even put expiration dates on it. It'll trigger exceptions or warnings to tell you, hold on a second, stop using that old name. You need to start using the new name. And this is getting more and more useful. And when you have access to all these techniques, especially if you come from the background of being a C or C++ developer, you kind of feel good about yourself. You can do a lot of really neat things that would otherwise be completely impossible in the very static world of C. In fact, from the perspective of a Python developer, there really isn't much to a C runtime. There isn't much going on. We will later on notice that that is not at all correct. And so you might feel a little bit of pride, and you might turn on your radio and listen to some Johnny Cash, and one of his other most famous songs is So You'll Know It's Me When I Come Through Your Code Base. And that's how you will feel about Python after I touch your code base. We'll do some things that might be a little bit questionable, but overall, there'll be some net benefit. We'll make use of all these safety valves, all these escape hatches, to really make sure that the system can operate as large systems do. But let's go a little bit deeper. Now, one misconception that we might have about languages that aren't Python is that they don't have the ability to do any of this, that C doesn't really have a runtime, that you can't do anything at all to patch a C program. But that's not quite correct. In fact, I had a real-world example of this very recently. It turns out I wanted to display this little clock applet on my desktop. And the clock applet was provided by Plasma, which is a new name for the KDE desktop environment. Every time I launched the clock applet, it would crash my window manager. I'd have to restart my window manager or forcibly shut down. Why? Deep in the code, well, how did I find this out? Well, I noticed at the terminal, when I'd run this application, it would say terminating current notification service with PID. So I grepped for that in the source code for the Plasma applets, and I found this is the one line with that string. And one line below, you can see they're calling kill on a process ID. They're accidentally killing the wrong process. Is this a mistake? I don't really know. I don't know the Plasma toolkit well enough. I'm probably not using it in the way that it's intended to be used. I'm trying to use it with my own window manager. Maybe you're not supposed to do that. I'm not sure. One thing that I could do is I could elect to, I have the source code. I could just build my own version of this. But I don't really want to do that because then I'll cut myself off from updates. I'd really rather find a more surgical way to patch this. Well, this turns out to be something that's very easy to patch in the world of C. What we can think is that this applet, this application, has some code that was written for that application. When that application was compiled, the code that was written for that application was turned into assembly code. Parts of that application that came from libraries, such as the kill function, which comes from a library for handling signals, were not statically compiled into the executable. Why should they be? In fact, we really want to have shared libraries because maybe that kill function has a bug in it or some security flaw in it. So we want to be able to update that without having to recompile all of our software, without having to download everything again. So what our application has to do is it has to dynamically bind to this kill signal. It turns out that whenever you start a C application or a C++ application, there's a process called dynamic linking. And what the dynamic linker says is, tell me all the symbols that reference code that you don't personally implement, that are implemented to some library, and I'll match them up. I'll make sure that when you call kill, it'll actually call the source code provided by your signals library, part of your C standard library that implements that. And it turns out that you can interpose, that you can interrupt this process very easily. Does anybody know how you do that? LD preload. So it turns out that you can write what's called an LD preload. It's a very easy thing to do. When your dynamic linker runs, it looks for a special environmental variable. That environmental variable is called LD preload. It should contain the path to a shared object, a small C program that you've written that doesn't contain a main, that's just a shared library. What it'll do is if that little shared object has any symbols in it, like a symbol referencing a function called kill, it'll first bind to that kill rather than the kill in the standard library. So here's a simple, this is what I did in order to solve the problem. I wrote a simple little LD preload. I implemented my own version of kill. If you tried to send sigterm, I would just say, no, don't bother, don't do it. Otherwise, I would call the real kill function and pass it along. So if my little clock applet, my little plasma applet, tried to call kill with an int signal or a hup signal or something like that, it would just happily pass through. If it tried to terminate a process, which is the behavior I wanted to stop, it would get trapped by my interposing function, something very similar to monkey patching that we see in Python. You can see this turned out to be pretty easy to do, but as the complexity of these things grows, it actually becomes much harder to write LD preloads. LD preloads are a real pain to write because you have to write them in C, and as Python programmers, we're not used to the more, shall I say, demanding and unforgiving nature of programming that we have in C language. And the way that we use this is, instead of running our program, we just run our program with an environmental variable. We give it the name of the shared object, and all the symbols in the shared object will take preference over something else. So you can see we already have a little bit of dynamic nature in C, but it turns out that this is not a very pleasant way to modify your programs. In fact, it's very unpleasant to do. You have to write a lot of C. There's a lot of boilerplate, a lot of pointers you have to deal with. It's really quite unpleasant. In fact, when I was doing this, it reminded me of another Johnny Cash song. If you haven't heard this one, I'm going to really get very frustrated because this is probably one of his most famous songs. And you can think of this whenever you're writing C code. It burns, burns, burns. The ring of fire. And that's kind of what programming in C can be like. It's a pleasant language. I personally prefer it over a language like C++, but it is a very tedious and very unforgiving domain. So why couldn't we write an LD preload in Python? I mean, we have a tool like Cython, which takes something that looks kind of like Python code and compiles it to a C shared object. I mean, when we create a python.py module and we have Cython compile it, that creates a .c file, which we can then use a C compiler to turn into a shared object. And the Python interpreter will happily dynamically load a shared object. This is how many of the modules in the standard library work. Modules like itertools, many of the modules that are written in C that are not compiled directly into your Python binary are actually just shared objects. And Cython gives you a way to do that without having to write the C. So why can't we do this? This would be a simple, shared object. It's kind of ugly looking. This is Cython Python. So you can see I had to pull out the dlsim function from dlf functions. I wrote my own malloc. So every time my C function calls, or every time my C program calls malloc, I just print something out. Why can't I do this? Well, it turns out you can't do it. It's not possible. You can't write an LD preload in Python. Dead stop. Because what will happen is Cython will build this code, presuming that an interpreter is already running. Your LD preload will try and call this exposed C function, which presumes a Python interpreter is running. it'll start doing things assuming that a Python interpreter has been started, where no Python interpreter exists, and no state has been set, and it'll segfault on you almost immediately. You cannot write an LD preload in Python. Except, it turns out, if you dig a little deeper, one of the themes I've noticed in some of the talks I've given is you dig a little bit deeper. So I gave a talk last year and previous years about embedding Python interpreters within themselves. And I showed how you can embed a Python 1 inside a Python 2 inside a Python 3 interpreter. And the trick to that was realizing that the DL open call that many of us are familiar with actually has a brother named DL mopen with an M in it that is very poorly documented, that sits maybe a couple lines down on the man page after your eyes glaze over and you decide to call it a night. Well, it turns out that you can't write an LD preload in Python, but you can write an LD audit in Python. Your dynamic linker, and I presume quite literally your dynamic linker, the dynamic linker on most of the computers in this room, as long as you're not on Windows, because we'll just exclude them from the conversation for the rest of the weekend, actually. Your dynamic linker allows you to audit. What that means is every time your dynamic linker goes out and tries to find a symbol, it'll notify you of what it's trying to do. And it turns out that one of the things it can notify you is when it's trying to bind a symbol. So you can actually write an LD audit in C, and in C you can try and understand what these arguments are. You know, the ref cook and the def cook sounds very important. As far as I can tell, the only thing that's really important is sim and sim name for these purposes. But every time you try and bind a symbol, every time your application tries to figure out where was kill implemented, where was malloc implemented, you can just get a notification. Not only can you get a notification, but you can step in and say, no, don't use that one, use this one over here. I'll show you something kind of interesting. Normally, what you would do when interposing or rather what you do when doing a symbol binding is you just return the symbol that was found. So somebody asks for malloc, you look around, you say, oh, malloc's over here. You give it to the program uses malloc for the rest of its runtime. I won't go into the way that the PLT works. There's a couple of other mechanics involved. There's some caching involved. There's this thing called the, what is it, the GPT? No, it's called the global, yeah, the GOT. I can't remember the acronym. And there's some mechanics there involved. But essentially, when your program tries to find a C function that it doesn't implement itself, it's implemented in a library, it has to go through the dynamic linker. You can audit that and have it give you notifications. What if instead of just returning the symbol, you embedded a Python interpreter into LD audit, and then you called out to a Python module? So every time your dynamic linker tried to say, where's malloc? Where's free? Where's my kill? Where's my dir open? Where's my f open? Where's my read? Where's my write? You got a little Python interpreter there, which will just resolve that for you. In fact, with just this one little piece here, you could end up writing your own dynamic linker in Python, in a Python module. Well, something really interesting happens when you write about 7 lines of, no, I take that as probably about 10 lines of C code to do this. And this C code doesn't really do anything very interesting. All I do is I look in a module that's specified somewhere for a function called resolve. I take my symbol name. I do a little bit of mechanics that are necessary in order to satisfy the way that functions are called in Python from the C layer. And I just call this function called resolve with the symbol that I was looking for, the name of the symbol I was looking for, and what would have been found otherwise. And then if it returns something that's not none, I just use that. Well, then I can write a really simple, not quite Python, but kind of Cython Python function called resolve that just says if the symbol name is open, that's the call, it's a syscall that opens files on a system and returns a file descriptor. Instead of returning open, return something else. Just store what was originally resolved, the real open call, and return my own function called open. Now you can see that this was very hairy, and this is why I got no sleep last night, because why on earth is it a long cast to a void pointer cast? First, we should already be in shock that we have these weird angle brackets in our Python code, much less that these are actually casts, much less we're taking a function pointer and casting it to a void pointer, and then to some CDEF type. It's nuts. And I don't know how I found that incantation, and I'm not sure why that incantation works, but just trust me, that's what you have to do. It turns out that things get much easier from here. Because then what you can do is you can just implement any C function that you want in Python. So here, this is just an implementation of your open call. Every time a program tries to open a file, it has to call the syscall open. That's the only interface that it has for opening files. It might call fopen, which then eventually calls open. There's no other way that it can ask the kernel to open a file. Well, it can do mmap and things like that, but explicitly for opening a file, the only way to do it is with this open call. Well, every time it tries that, my Python code just prints out what arguments are passed. It's kind of like strace, like a really wonky strace. The neat thing here, though, is this is not quite Python. It's Cython, but it follows kind of the same rules. And I can program it with the same, I'd say, convenience that I can program normal Python. So you can see, I'm just using advanced string formatting. I don't care what the types are. I'm not allocating any memory. This is actually, except for a couple of small pieces, like having the types here and having the CDEF at the front, this is more or less very standard Python. Well, one interesting thing that I could do is, because that's really boilerplate, I could write a decorator. And the decorator, I could just call it preload. And I could use the annotations feature in Python 3. And I could just write something that looked almost exactly like pure Python that generated the Cython-like code, built it, and what you'd end up with is you could write in pure Python without any knowledge of anything else. You could replace any C function in any program anywhere. Now, this was supposed to be the set piece of the talk, and when I presented it to a couple of people late last night, I felt they didn't quite get it. And so I had to come up with a compelling example for that. I'll show you an example. I like to find very trivially simple solutions to common problems that we have, so trivial that you look at that and you say, well, hold on a second. I can't really tell that there's something there, but suddenly all these mechanisms that I had before I don't need. So one thing that I like to do is, especially if I'm deploying code, I want to check new code against old code. I want to make sure the results are the same. And so one thing that you might do is you might check out the old code here and check out the new code here. But that can be very clumsy. Another thing I might do is I might add into my program some ability to say, oh, this is the new module, this is the old module. Just pull the old function out of the old module and new function out of the new module and compare them. Well, some of this comparison and diffing mechanisms already exists in the form of my version control system, Git. If I really wanted to be very simple about that, every time I made a change to my code, I'd have one branch of my Git repository with the code as it stands, and one branch that I'm waiting to merge in with all the changes that I want. And I just check out one of these branches over here and check out one of the branches over here and run my application in parallel. But I wouldn't do that because it ends up being very clumsy. And I have a lot of physical artifacts, and it's kind of hard to script because if the checkout fails or if there's something that has to be stashed, it'll just kind of blow up on me. However, one way that I can get around physical artifacts is there's a library called libgit2. And I have no clue how to use libgit2, but there's Python bindings for this. This is a common theme for me. I find that I'm just too lazy to learn enough C to really write C. I'd rather write Python. And even though PyGit2, which is just a library for interacting with the Git repository, has very similar API to libgit2, when I'm playing with PyGit2, I can do dir and help, and I can kind of futz my way around figuring out how to use it. Whereas if I were writing this in C, I'd have to spend a lot of time in man pages and documents and manuals, and it would be very unforgiving. So you can see here's a simple example of what you can do with libgit2. You can initialize a repository, you can get the head of the repository, and you can iterate through all the elements, all the objects, all the blobs, all the files in that tree. And you can do that without checkouts, without any physical artifacts, without shelling out to the command line. What if I combine these two? What if instead of catting a file to my standard out, I could pass in my LD preload with a commit hash, and it would cat the file as of that commit hash. Cat, which doesn't know anything about Python, which doesn't know anything about Git, is now Git aware, right? I can make any program, and how do I do that? Well, let's think about that. And I might simplify it, and this is how I actually simplified it. I have a little thing called Git, and you give it a commit hash, and then any program after that only sees the state of the file system as of that Git hash. And that shouldn't be too hard to do, actually, because you can think that any program that interacts with the file system has to go through system calls. Open, close, read, write, stat, the 64-bit version of those, a couple more, and you have to spend a little bit of time with man pages. Well, it turns out you don't have to spend a lot of time with man pages, probably about on the order of 15 minutes per system call. I tried this because I had a little bit of downtime earlier. And you can take any program that was never designed to do anything with Git and just tell it every time you try and open a file, no. Use my open function over here that opens the file via the Git repository without any physical artifacts. One thing that I want to do that I didn't have time to do that I expect will take about 30 minutes is I want to write an LD audit. And I'm not writing any C code anymore, by the way. I'm writing kind of C-ish Python, but with my decorator, I don't even have to write that. The only thing I have to know is the man page and what the original signature of the C function is. But outside of that, I don't have to write anything that doesn't look like anything but Python. Well, Python is a really rich standard library. I can interact with zip files very easily from Python. Why don't I just write a little hook? So every time you open a file, if it's a zip file, I just transparently unzip it. Suddenly, every single application on my computer doesn't even have to know what a zip file is, transparently can read and write from zip files. That's kind of powerful, isn't it? This is actually very similar to Fuse, except instead of implementing a file system in user space, I've implemented something akin to a file system in process space. And you can start to do some really neat things. I joked with one of my friends who I show some of these things to, but he's a JavaScript guy. And I said, you know what you can do with this? You never have to minify your JavaScript to disk again. Just write a little shim, and your web server will just minify it when it opens. Every program you have can minify it on open. You never have to store the minified JavaScript to disk again. You do some really weird things here. If anybody here remembers server-side includes from the old Apache days, you could do something like that. You could have files that exist on disk in one form, and under certain processes look in other ways, automatically generate themselves, automatically template themselves. You do a lot of really neat things. Things which we could do with Fuse, but would be very inconvenient. Thing is, you could do that with writing only Python. And in my experiments today, with a 5 minutes downtime here, 10 minutes downtime here, it is exceptionally easy to write this in Python. So no doubt, I don't expect it to take more than 30 minutes for me to write my zip file loader, and then every single program, my ls, my cat, my head, my vim, my open office, my web browser, are now able to read and write to zip files without even having to know they're zip files, without even knowing anything about what's going on, because I've interposed the system calls, and because the only way for them to interact with the system is via those system calls. And I can do it very easily, because I can write it in Python, and I get nice error messages. I don't get seg faults all over the place. I can print things out. I don't have to worry about types. I don't have to worry about memory allocation. Sure, I get a little bit of slowdown here and there, but the power is worth it. So that was the set piece for this talk. And I'll give you a small example. I created a really simple Git repository. There are actually 5 commits in it now, but there are 4 commits. I had a single file, and I changed it 3 times. And so you can do something just as simple as this. This is the file with this commit hash. I can cat the file with a different commit hash. I can cat the file with another commit hash. And you can see cat has no clue that there is a Git repository. It has no clue other than there's files on disk that I'm opening and reading from. It's my little helper there that's written in Python that is now intercepting all of these system calls and doing something with it. So this is something that I thought was kind of exciting. I hope that you can appreciate it. And you can see this is what the original file has. And if you feel like you don't quite understand it, but it seems cool, I guess that's enough. If you're not a fan of Johnny Cash yet, I have one more of his most famous songs to share with you before we conclude. And you might ask me why I did this. And you might ask me why I do any of these things. And the reason is I just do them for the sake of doing them. Just like Johnny Cash, when he was a young boy, his mom told him, don't ever play with guns. Oop, let's get this one up.
Boy, don't ever play with guns, but I shot a man in Reno.
Just to watch him die. Although sometimes I must admit, when I hear that whistle blowing, I hang my head and cry. So that's Python and Johnny Cash. A little bit of subversive Python. I hope you enjoyed it. I'm James Powell. I think we're finished a bit early, so if anyone has any questions. Who wants to listen to a little bit more Johnny Cash? Oh yeah, let's get to city project speaking, Johnny Cash. Okay, any questions? You know, the interesting thing is if I don't want this video on YouTube, I'll play more than 7 seconds of any of these songs because they'll automatically block it, so I should be a little bit more careful than that, right? Any questions, any thoughts? It's a very interesting technique. When I first discovered it, I thought, this couldn't be useful at all, but now I'm realizing that you could do a lot of really absurd things with it.
This isn't really a question, but I recall a talk at PyCon a few years ago, a company that did testing of Windows products, for which they didn't have the source code or even know what language it was in. But they did pretty much the same thing, in the way that they can hack into any Windows or DLL call, replace it with Python.
With Python I think the Python element is the
It would directly run with Python. They injected the interpreter as well, so they could run any Python or any system call, DLL call, and they use that for testing for.
So I think the Python dimension is what makes it most impressive. Being able to intercept calls. Windows has their own mechanisms like detours for doing things like this, but being able to do it conveniently and being able to turn around like an LD preload in 30 minutes to an hour is quite
They also
amazing.
found that they could that it would completely bypass Windows security, so they could.
Oh, that's fantastic.
Any system, whatever the user was, whatever the permissions were, they could hack into any system.
Oh, that's amazing. That's fantastic. That's what they
They didn't reveal the details of how they did it because they thought it was too dangerous.
maybe I should I'll show you some. Maybe I'll give a lightning talk tomorrow. I'll show you some wild stuff. I'll show you some wild stuff that you can do. Python is a very permissive language. So, one thing I've always wanted to do is you can think that Python is used for very big systems, and sometimes in those systems you have memory that you don't really want people to be poking around. You can do things like lock memory pages so they don't get paged to disk. What I wanted to do for a long time is create a type constructor that can wrap any type to make sure that type never gets paged to disk. So then you can create your own custom password type, and it would never get paged to disk, which in some applications would actually be a legitimate security concern, that if these secure credentials ever get paged to disk, then we lose something.
What would be to stop you from copying something from that object to a non-function?
So I think that there's I think there's a problem because sandboxing Python is a very difficult thing to do. I have my approach for sandboxing Python. In my approach for sandboxing Python, I patch the ceval loop, the main interpreter loop. So every time you try and push an element to the stack that you're not supposed to look at, it blows you up. And for the most part, I can't figure out any ways around that. It also allows you to. Has anyone seen that one? That one's really neat. You want to see that one? Let's see if I have a working version of it. What was it called? Read watches. Python. Okay. Do I have internet access? Source install. Python 3. Let's pip install it. Bin Python 3 pip pip 3.
James, can you
Yeah?
use this to intercept system calls to play Johnny Cash songs whenever a system call is made?
If you wanted to. Let me stick this in my Anaconda Python maybe. Pip 3 installed. Okay, there we go. Let's see if this builds. This one was really neat. Did that fail? Oh, that failed because it's not the right version of Python. Maybe I need a Python with pip. Does this have pip? Yes, this has pip. Dev, pip installed, drt. This one was a really pip3. No, that one failed. Unfortunately, I'll have to show it in the lightning talk, but I have this thing called read watches where you can intercept things where they're pushed and popped to the Python stack. You do all sorts of really, really wild stuff with that. You can implement pointers in Python. You can do sandboxing in Python. You can do lazy loading in Python. You can really, really wreck the way the interpreter works. And you can, the reason for that was, and actually the initial intention of this talk was going to show you how you can use some of these patches in a CPython interpreter to implement better debuggers. I think that some of the crazier patches that you might have are things which you might not feel comfortable being able to get right in production. And so you might wonder, should I really do this if I can't get it done perfectly? However, I think there's, in the course of our work, there's often some area where we have a lot of flexibility in terms of the correctness of the solutions we have. Often that's in a design phase or a debugging phase. And so one thing that I've wanted to do for a very long time is collect a bunch of patches to a CPython interpreter that allow you a couple more hooks solely for debugging purposes. Read watches would be one of those. And so what you could do is you could tag a variable so that anytime that variable was looked at, or anytime that object was looked at, it would trigger a callback. And you could figure out if you had some large data pipeline with millions of objects, but one of them was malformed in some way, where it was being caught along the line. This is similar to what you have in a language like in GDB with read watches as well. It's something that which you cannot currently do in Python. And you could do some really nice debugging. You could have debugging on par with what you can do. You could do things like, if anybody here's a user of PDB, PDB is so limited because it's designed for a very static form of debugging that's appropriate in C or C++, which is not appropriate in Python. So how do you put a breakpoint on a lambda in PDB? Kind of breaks on you. Well, you could use read watches to put breakpoints on lambdas, right? Which is a very reasonable and desirable thing to do. Any questions? Did anyone have any idea what I was talking about the whole time? Oh, except when I was talking about Johnny Cash. Very good. Well, I don't want to keep you folks any longer. I hope you've enjoyed this amazing day at PyData. I hope to see you all tomorrow. Maybe I'll give a lightning talk if I can find a version of the code where the read watches work. Otherwise, please enjoy your afternoon. I think we're going to the pub in about 15 minutes. If you like this talk, I'd love to chat with you more. If you do any of this stuff, if you get paid money doing any of this stuff, I'd love to talk to you, because I actually think that there's some real legitimate business value here. It's just that it's difficult to find organizations that have the, shall we say, the stomach for it. Thank you so much.